delay of 5 minutes. So let me call up to Brian for his final lecture on this mini course series.
Thank you. Good. So no lectures tomorrow, is that right?
I don't think so.
Okay.
There's rain.
Right. So I wanted to give kind of a number theory application of some of the combination of random matrix theory and moment calculations that I've been doing earlier in the week. So we start with this classical problem. Which integers m are the sum of two rational cubes? So we want a positive integer m as say r cubed plus s cubed, where r and s are rational numbers. And so m equals 1. Is that a sum of two rational cubes? Anybody? What? Okay, what if I say positive rational cubes? Actually, I wonder if I did this right. I think one word would be a violation of Fermat. Yeah, so one is not. 6 is. 6 is 37 over 21 cubed plus 17 over 21 cubed. So if you like, 37 cubed plus 17 cubed equals 6 times 21 cubed. And well, 346 also is. And that's actually the smallest way to do it. Here's a table by Selmer up to 166. He was very, very interested in this. I don't know how well you can read that. It's kind of small, but you see 6, 7, 9, 12, 13, 15, 17, and so on. And over here, you actually see sometimes there's a 1 and sometimes there's a 2. With 2, you kind of have two distinct in some way, kind of independent in some way, solutions for this. And basically, we're going to apply sort of random matrix theory and moments of L functions to try to say something about this. By the way, the work in this talk is it's joint with Keating, John Keating, Mike Rubenstein, and Nina Snaith for most of it. This part actually is due to Mark Watkins, who was building on the stuff that we did. And in this Selmer case, it's something Gauss was also very interested in. Basically, let's just suppose m is square free, so we don't have to worry about it. And we want to know if m is a sum of two rational cubes. Well, it's believed that if m is congruent to 4, 7, or 8 mod 9, then it should always be. Okay, so that should always work. Whereas if m is 1, 2, or 5 mod 9, then every once in a while it works, but it's actually rare. Okay? And so we want to actually focus on m's congruent to 1, square free m's congruent to 1, 2, and 5 mod 9. So the rare case, and hope that random matrix theory says something about that. And just to give you an example, so Mark Watkins computed the data for the rare m, in other words, the 1, 2, and 5 mod 9, and in particular sorted those m's further into congruence classes mod 7. And in particular, if you look at 2 mod 7 and 3 mod 7 and compare them, you see that in these sort of rare times, looking at these things mod 7, they're not evenly distributed over the residue classes mod 7. And in fact, if m is 2 mod 7, then up to 1 million or 10 million, there were 125,000 values of m for which there were solutions, but only 59,000 values of m that are 3 mod 7 where there's solutions. And in fact, random matrix theory and analytic number theory lead to the conclusion, the conjecture that Watkins made, that in fact this ratio is exactly 2 to 1 as m goes to infinity. So exactly twice, well, I mean exactly, in the limit, as m goes to infinity, twice as often a number congruent to 2 mod 7 will be a sum of 2 rational cubes as a number that's 3 mod 7 when we look through square-free m's that are 1, 2, or 5 mod 9. Okay? So I like this because it's nice and clean, and anybody can basically understand it. Yeah.
This allows for x or y to be 0, or no?
Well, actually, that doesn't matter, because if one of them is 0, then the thing's a cube, and
If, for example, the first line, if m is a cube, if m itself is a cube, it could be congruent to 8 mod 9, right? And
right.
If one of them has to be 0, otherwise you're violating.
Yeah, that's right. But that's going to be a small, that'll be a small chunk of things, right? The cubes, if m is a cube up to...
You're saying that there's always a solution. The first 3 lines.
Oh,
There will always be a solution. If you get m congruent to 2 mod 9, you get m cubed congruent to 8 mod 9. So the solution has to be with x 0.
let's see. Sorry, I'm not following exactly what you're saying.
9k plus 2.
So you think I'm lying in the first 2 lines, is what you're saying?
No, I'm saying it's okay as long as you allow for 0 solutions. If you get a number nk plus 2 and take it cubed, m is the cube of a...
No, it's a rational cube, right? So not an integer cube. So these are not integer solutions, they're rational solutions.
okay.
Yeah, x and y are rationals, right. Okay, yeah, they're rationals. So it's not quite, yeah, it's not a sum of 2 integer cubes, just a sum of 2 rational cubes. And so it's really the sort of, yeah, x, so in integers, think of it as x cubed plus y cubed equals m times z cubed. And the rarity, how rare? Well, around x to the 5/6 of the time is how often you expect there to be a solution. It's actually x to the 5/6 times some power of log. Okay, so where this comes from is, well, there's elliptic curves here. I haven't said anything about elliptic curves, but really x cubed plus y cubed equals m is an elliptic curve. And what we're talking about is ranks of elliptic curves. And you get a family of elliptic curves as m varies, x cubed plus y cubed equals m. M is sort of the parameter for a family. And with elliptic curves, you have L functions, and you have something called the Birch, Swinnerton, and Dyer conjecture. With elliptic curves, you have a group law. You can add points on elliptic curves and get, add rational points, for example, on elliptic curves and get more rational points. And you get a free, or you get an abelian group, finitely generated abelian group. The number of generators is the rank, and the rank by the Birch, Swinnerton, and Dyer conjecture is supposed to be equal to the order of vanishing of the L function. And so we're going to approach this by, well, I mean, we're making a conjecture, so we're allowed to assume anything under the sun. So we'll assume the Birch, Swinnerton, and Dyer conjecture, and we'll assume the moment conjectures about a family of L functions, and et cetera. But in the end, you wind up with this very clean conjecture that has no reference to elliptic curves, to random matrix theory, to the Birch, Swinnerton, and Dyer conjecture, to moments of L functions. But this all comes out of it. So that's why I like this. Okay, so now we're not actually going to deal with that problem. Instead, we're going to look at quadratic twists. So we're going to look at a family of quadratic twists of a fixed elliptic curve. And so we'll just take an elliptic curve in this Weierstrass form. Y squared is x cubed plus ax plus b, let's say, where a and b are integers. And, oops. God, did I mess up my slides again? Okay. The rational points, when x and y are rational on your elliptic curve, can be added together. There's this group operation, and you get this finitely generated abelian group. I think this is, I hope I've got the right slides here. Right. And as I said, the rank is conjectured to be equal to the order of vanishing. Here's an example of y squared equals x cubed minus x plus 1 of illustrating the group law. And so you have a point P, a rational point. When you plug in x is minus 11 ninths and y is 17 over 27, this satisfies this equation. And same, well, with 0, 1, that's obvious. And in the case that your elliptic curve really does have a form y squared equals a cubic in x, then you can find the sum of the two things by, well, you just join p and q together with a line, and that line will intersect the cubic in a third point that will also have rational coefficients. And then you reflect that about the x-axis. And that's your sum, p plus q down here. So that sort of illustrates the group law. And so once you've got a point, you can also do it with a tangent line. Once you've got a point, you generate an infinite number of points, as long as it's not what's called a torsion point. And so you generate this infinite number of points, and then that might exhaust all the rational points on the curve, or there might be another one someplace. And if there's another one someplace, you can do the same thing and repeat that. And as many of these independent points as you can find is the rank. And that rank is known to be finite. Okay, yeah, so I already said this. But yeah, the group is finally generated. The rank of this group is conjectured to be equal to the order of vanishing of the L function of the elliptic curve at the central point. So what is the L function? Now, okay, so for all the past lectures, my L functions all had s going to 1 minus s, which is kind of the analytic normalization. But here, it's a little nicer maybe in some situations to have the normalization with s goes to 2 minus s. And then we have integer coefficients for these APs. So the L function can be written as an Euler product. So there's a number q, the conductor of the curve. It has the same primes as the discriminant, so you can actually think of it in some sense as a discriminant of the cubic. And you have an Euler product with a sort of a degree 2 Euler factor. So the degree is 1 over p to the s, and then 1 over p to the 2s, so 1 over p to the s squared. So this is degree 2, and degree 2 L functions have sort of degree 2 Euler products. The degree of the L function sort of matches the degree of the Euler product over here, and matches up with sort of what we call degree in the Selberg class with the gamma factors in the functional equation. And then you have, it behaves differently for a finite set of primes, the primes that divide the conductor. And the AP here is just p plus 1 minus np, where np is the number of points that satisfy the equation of the elliptic curve over the field of p elements, as we saw in John's talk and Zania's talks. Okay, and we know now that for any elliptic curve that this L function is entire and satisfies a functional equation. The L function is associated with a cusp form, a modular form on gamma naught q, let's say, in here. And it satisfies a functional equation like this. The coefficients are always real, and so you have this number, this sign of the functional equation, which can be +1 or -1. There's a conjecture, yeah. So if W is -1, then the order of vanishing if W is +1, then the order of vanishing of L at 1 is going to be an even number. And if W is -1, then the order of vanishing at 1 will be an odd number. And so by the Birch-Swinnerton-Dyer conjecture, that order of vanishing should be the same as the rank. And so if W is +1, the rank should be even. And if it's -1, the rank should be odd. That assertion is called the parity conjecture, which is weaker than the Birch-Swinnerton-Dyer conjecture. Okay, now we're going to start with a fixed elliptic curve, and then we're going to be interested in a family of quadratic twists. So D will be a fundamental discriminant, and chi d of n the Kronecker symbol. If D is P, then basically it's the Legendre symbol, which is +1 when n is a square mod P, and -1 when n is a non-square mod P. And you can take your L function and twist it by this chi d of n, which just means multiplying the coefficients in the Dirichlet series by chi d of n, this +1 or -1, or it's 0 if n and d have a factor in common. Then it turns out that this is just the L function of the elliptic curve, let's say, associated with E sub d, which you can write down as just dy squared as x cubed plus ax plus b. And then that has a functional equation, and it looks very similar to the functional equation that we had for E, except that now there's a d here and here, and there's the original sign of the functional equation, and there's a chi d at minus q will be a factor now in the root number. Okay, so what we're actually going to be interested in is we're going to be interested in sort of when I said the rare situation. That's a situation we're going to be interested in, the situation where the sign is +1 in the functional equation. So that if you get vanishing, then it should be an even vanishing, and so you should be looking at rank 2 elliptic curves. So what we're trying to approach through what I'm saying is how often in this family of quadratic twists of a fixed elliptic curve do you get a rank 2? Do you get rank 2 or higher, rank 2, rank 4, rank 6, whatever? So the belief in general, which I think was first phrased maybe by Goldfeld, is that if you look over all elliptic curves, basically if the root number is +1, then almost all of those have rank 0. So no rational points of infinite order. And if the sign is -1, then almost all of those have rank 1. Okay, so ranks 2 and higher for elliptic curves are rare things. And what this is intending to get at is the frequency of rank 2 curves among the quadratic twists of a fixed elliptic curve. And so when we do this, we're going to restrict our attention to when this number is +1, okay, which then is just an arithmetic progression of d's mod q, okay, or a union of arithmetic progressions. Like if w is +1, then we just want to look at our family of d's for which chi d of minus q is +1. Or if w is -1, then we want to look at the collection of d's for which chi d of minus q is -1. Q is fixed. It's the conductor of your original elliptic curve here. And so the d's that we get in this family that we look at will be a union of arithmetic progressions mod q. Okay? And, okay, so, yeah, so I think I already said all this. Okay, now I think for the rest of the talk, I just want to fix attention on just one specific, or at least for a while now, one specific elliptic curve. We'll just take the first one, E11 we'll call it, or just E. So that's kind of that's the elliptic curve of smallest conductor, conductor 11. It's kind of the first curve that you find. If you look at Cremona's tables, which are now in the LMFDB, and you search for elliptic curves, this is the first example. Okay. And well, one way to write down the equation, it doesn't actually look now like y squared is a cubic in x. It's y squared plus y is x cubed minus x squared. I think it has to have a model that's y squared is a cubic in x with integer coefficients, like I said, but I don't actually know what it is. I tried to find it during John's talk, but I couldn't. Sorry, John. So NP will be the number of solutions, the number of mod p points, x and y, such that y squared plus y is congruent to x cubed minus x squared mod p. So you can calculate that easily for small primes. And then the AP that we want is going to be p plus 1 minus np. And then the L function that you make, it has a factor for 11, and then it has another Euler product where you put in these APs that you calculated. And that gives you multiply that all out, and you have a Dirichlet series. And that's the L function of E11. Now, this is just sort of an aside, but sometimes cusp forms, sometimes modular forms can be expressed as eta products. We saw that in several talks already this week. And in particular, this one also has an eta product. So that might be a shortcut way to generate the ANs. So basically, one way to think about this is, so the L function, the elliptic curve is associated with a modular form of weight 2 and level 11, where you can find all those things. Go to the LMFDB, for example, but it's a finite collection of things that are Hecke eigenforms, things with multiplicative coefficients, basically. And this eta product, which is essentially eta of z squared times eta of 11z squared, I believe, is also a weight 2 cusp form on gamma non 11, and so you just have to compare the first few coefficients to verify that, in fact, this is correct, that it works for all the coefficients. So anyway, this would be a sneaky way to calculate the ANs as the number of solutions, p plus 1 minus the number of solutions. Just multiply out this product, and you don't have to, you don't have to do all that other work. Anyway, so the functional equation is this. Oh, I forgot to change that 1 into a 2. I was converting. No, I actually, I originally had everything scaled. S goes to 1 minus S. And I went through and changed it all, but I didn't change that one. Yeah. Anyway, so that's the functional equation. So the sign is plus 1. So the W is plus 1. And now if we want to do the quadratic twists, okay, then it'll look like this. Now you just have a chi-d AP here and a chi-d squared. And it's going to have this functional equation where the sign of the functional equation is now chi-d of minus 11. That n should have been a q, and that q should have been an 11. So chi-d of minus 11. So we're going to actually look at a family of, we're going to look at the family L sub E11 of S chi d such that chi d of minus 11 is equal to plus 1. Okay, and then this corresponds to, hopefully I have it written on another slide, which d's that is, otherwise oh, let's see. I guess we can just do that by, let's see, quadratic reciprocity, right? So the Kronecker symbol is d over minus 11. We want that to be plus 1, right? Which means, let's see, can I do this in real time? Equals minus 11 over d times minus 1 to the, so minus 11 is congruent to 1 mod 4, right? So we don't need, okay, I don't know if I'm doing this right or not. So minus 11, d over minus 11. Oh, no, I was better off leaving it just, yeah, I was better off. Okay, no, I'm not going to do this calculation. Okay. All right. Anyway, now the key thing here, a key ingredient to this is that, okay, so this is going to be a family of L functions. And I think I forgot to say it, but I think I had it on an earlier slide when we were talking about symmetry types of families. If you start with a fixed cusp form, L function of degree 2, basically, and you twist by quadratic twists, then you wind up in an orthogonal family. So this family that we're going to look at is going to have an orthogonal symmetry to it. So we'll be comparing statistics of this family with statistics from, actually from the even orthogonal groups. Okay? And it turns out that, that for many L functions, there are formulas for special values, like the central value. And I'm not an expert on that, but so for degree 1 things, you never have any formulas like that. But for degree 2, basically you do. There's going to be some formula, and for degree 4 and so on. So it seems to me that for even degree L functions, there's always going to be some sort of arithmetic formula for the central values. Now that's not 100% true, but I think it's kind of a guiding thing that's more or less true. And in any event, in this case, there are formulas. So this goes back to Shimura and Balsberger, and in this, Bergstrand and Dyer, and in this case, it's actually Konen and Zagier gave formulas for how to find the central value of an L function associated with a cusp form in a very concrete way in terms of things like, so actually there's a theta series that I'll say in a minute, but this C11 absolute d squared, this is an integer, okay? And this kappa 11 is a period, right, Xenia? So yeah, I don't know exactly what integral to write down to get this thing. I mean, it should be that kappa 11 is a period. Now, it should be something like a dx over y over some path. And here we've got, I don't know, y squared plus y equals x cubed minus x squared. Maybe it's not exact, maybe it's twice it or something. It's some simple constant times a period. I'm not quite sure how to calculate that. Wait? I think it's pretty simple, but, right. But yeah.
Digging into my memory,
Yeah.
it might be the elliptic integral of the 11th singular value, which by the Chalmers-Selberg's theorem is expressible as a product of gamma of...
Oh, right, but that would be a very special case, though. But in general, it should just be whatever number. I mean, you have this kind of formula. This formula is not special for E11. You have a formula like this for whatever. But yeah, in the Chalice, yeah, that's right. So that could be a product of some gamma. You're right. Okay. Anyway. Right. I should have. Yeah. Which I don't actually know how to get this. But at any rate, you have this. And now, so the thing is that this C11 of D is an integer. Okay? And so that means that the L values at the central point here, as you run through this family, are sort of quantized. I mean, they can only be, very specific things. They can only be 0 times kappa 11 over root D, or 1 times it, or 4 times it, or 9 times it, whatever. Okay, and so somehow or other, so you have this, on the one hand, we have all these statistics, right? We're trying to compare L functions with random matrices, with random matrix groups. We want to compare this with, SO2N, whatever. And there, obviously, everything is nice and continuous. You can have whatever values you want for, this would be like the value at the point 1 on the unit circle, for the characteristic polynomial. And as you range over all the matrices, obviously you can get basically any number you want, from 0 all the way up to like 2 to the n. But here, we have this discretization. And so we're trying to model this number theoretic situation by, by random matrix theory, by this continuous thing. And we can actually use it to our advantage. So basically, I'll just tell you the punchline right now. What we're going to do is we're going to look at the moments of L, E, chi D, and not just integer moments, but actually real and even complex moments. We're going to look at all the moments, sort of the moment generating function, if you like, that Keating and Snaith calculated. And from that, you can invert that and get a distribution of values. And then we're going to say, well, we think the L function moments behave the same way. And then we're going to calculate the probability that the L value is smaller than 1 times kappa 11 over root D, because if it's smaller than 1 times it, it has to be 0 times it. And then that's a probability that the L function vanishes. It's an even L function. The sign is +1, so it must vanish to order 2. And so the associated twisted elliptic curve should have rank 2. Reasonable thing to do. Okay, so, all right, so let's do it. Oops. Okay, oh, by the way, so Gross actually calculated specifically what the theta series is for this particular case. Well, it's a difference of 2 theta series. And they're given explicitly like this. They're ternary quadratic forms, which give weight. So they're basically weight 3/2 modular forms, and this is exactly what they are. And so by the way, once you know what those are, you can generate an enormous amount of data, right? Because you compute this C11s for hundreds of millions of values of n, and then pick out when it's, in the cases you're interested, when it's at 0, and that gives you the 0 values that you're interested in. So we're going to have a prediction from random matrix theory, but we're also going to have a ton of numerical data by calculating these theta series. And actually, we've done this with like a couple thousand different elliptic curves, not just this one. And Gonzalo Ternaria, who disappeared for this lecture, actually is the person who calculated all the theta series for these things. Okay. All right, so the thing we're interested in then is the nth moment of the characteristic polynomial of the matrices with Haar measure over the orthogonal group. And this is the formula that they got using Selberg's integral. And the key thing that we need from this formula is that the pole that's furthest to the right is at s equals minus a half. And that comes from this factor right here. When j is 1, it'll be s plus a half, and the gamma function has a pole at 0, and so the pole will be at s equals minus a half, right? So that's the first pole. That's the pole that's furthest to the right of this thing, is s equals minus a half. And so that's kind of a key thing. I should have also put on this slide, but I didn't, what the residue of this function is at that pole. That's a slightly complicated thing, right? Because you have to take, well, calculate the coefficients of all this. And that basically turns out to involve a Barnes gamma function and introduces sort of a log power of n into the thing, or an extra power of n, not of log n, but of n into this. But anyway, so this is their formula. And if you want to invert that, you can basically do, well, something like a Perron's formula, or just put a delta function in, whatever. But so the probability of the characteristic polynomial having a value alpha is essentially this. So that's inverting this moment generating function, okay? And C here is bigger than minus a half. And so what we're going to do is just move the path of integration. We're thinking of alpha as being small. And we're going to move the path of integration off to the left. And so cross that pole at c equals minus a half. And so we'll get an alpha to the minus a half. So alpha to the plus half over that alpha will be a 1 over square root of alpha. So we get an alpha to the minus half. And then the sort of residue calculation, the messy kind of thing, results in this. This is the Barnes G function. And there is a power of n that comes out of this, n to the 3/8. So when you calculate the residue of this thing at s equals minus a half, this is what you get asymptotically. Okay, so you can just think of it, as a constant times n to the 3/8, basically. Okay, and then now the L function, oops, I didn't change these halves into ones, sorry. These are ones. Okay, L of 1 chi d less than 1 times kappa over root d implies that L is 0. Okay, and using that SO2n as a model with n of the size of log d suggests that the probability that the L function is less than x should be, well, okay, so some constant times a sub minus 1/2, that's the arithmetic factor, and then times log d to the, so log d, n is log d, so the n to the 3/8 becomes a log d to the 3/8, and then the alpha that we're using, so in here, alpha is going to be like 1 over square root of d, right? The alpha that we're using is, we want to know when is the L function smaller than kappa over square root of d. So the alpha is like 1 over root d. So alpha to the minus a half then is, alpha to the plus 1/2 then is 1 over square root d to the 1/2, oops, which is 1 over d to the 1/4, okay? So for an individual one, the probability, oh, I have x here, but that should be probability this is less than kappa over root d. So with x, sorry, this should be kappa over root d, then is d to the minus 1/4. And let's just restrict our attention to d equals p, okay, primes. And so then if you sum this over primes and ask how often you get a prime twist with a double 0, when you sum this over p's, there's x over log x p's, and then you have the extra log to the 3/4, you end up with, so x to the 3/4 times log x to the minus 5/8 values of p. And so that's our conjecture, is that L function, or really any quadratic twist family of L functions twisted by primes, should have rank 2s in around x to the 3/4 log x to the minus 5/8 values of p. Okay, and let's see. As I said, we did a ton of numerics on this. So this is 55 curves, and it's just comparing the number of rank 2, or the number of even rank curves in twists up to 100 million, and dividing that number by x to the 3/4 log x to the minus 5/8. And so this is 55 different curves. Now, we're not actually able to pick out so we think the answer should be asymptotically some constant times x to the 3/4 log x to the minus 5/8. But we can't quite, we know some of the ingredients that go into the constant in front of it, and that constant depends on the elliptic curve, which is why you have all these different things. But what you're supposed to be looking at is that they're all flat, right? And so we don't actually know what that constant is, which is, we really wish we did, but we don't. And here's, okay, now this is so this is with using 2,000 curves, same sort of thing. You see some kind of funny, some things have really big constants and some curves have really small ones. And this actually gets into a little bit some work that Christophe Delaunay has done with looking at modeling the distribution of Tate-Shafarevich groups according to what they look like, using the Cohen-Lenstra heuristics for probability for looking at how abelian groups with certain structures are distributed. And so that comes into it a little bit, as well as some other random matrix theory. But at any rate, now it's a little hard to parse that last slide. You look at something and, well, is that flat or is that not flat? Well, this is the distribution of the slopes from the last thing. And so the slopes of these are like, this is 10 to the e to the minus 10, or maybe, let's see. Does that mean e to the minus 10 or 10 to the minus 10 to the minus 10? Yeah. So they're really flat. They're really, really flat. Okay. Now, we did, so now this is getting more towards what I began with, which was this, sum of, when is M a sum of two rational cubes? And the punchline in that was, well, we decided to compare M's that were congruent to 2 mod 7 with M's that are congruent to 3 mod 7. So in other words, you're twisting by this whole bunch of chi-d's, restricting to chi-d's so that you get a +1 in the functional equation, and looking for when you vanish. But so you have this whole set of d's, mod q or whatever, a union of arithmetic progressions mod q. But now take some other prime that's completely unrelated, and split those d's up, mod 5 or 7 or 41, whatever. And are the vanishings, the rank 2 things, are they evenly distributed throughout these arithmetic progressions? Well, it turns out they're not. So in that Watkins case, the arithmetic progression 2 mod 7 was twice as likely as the arithmetic progression 3 mod 7. Okay, and that occurs for all of these things. And in fact, what we discovered just empirically, just looking at the data, is that the d's mod p, you look at whether or not d is a square mod p. And through all the residue classes where d is a square mod p, you get basically the same frequency of double vanishings. And for all the d's that are non-squares mod p, you get the same distribution. But those two numbers are different. And if you take the ratio of those two numbers, then you're taking a ratio of basically some constant times, x to the 3/4 log x to the minus 5/8 divided by another constant times that same thing. Well, the constant that, the unknown constant that's in front of the whole elliptic curve thing cancels out. And so you actually wind up with a precise, beautiful result that doesn't have any unknown constants. So this looks complicated, but we're basically counting rank 2s. So you fix an elliptic curve, twist by the d's, the chi d's, for which you get a +1 in the functional equation, and count how often you get rank 2s, and split those up into, take a prime p, your favorite prime p, fix it, p equals 5 or 7 or something, and then look at the d's mod that are square mod p versus the d's that are non-square mod p. And that's what this ratio is. These are all conditions on the sum. We're just summing 1. Okay, and what happens is, so now you do the exact same calculations as before, but you're restricting your family of L functions is now further restricted by another condition that the d's are squares modulo 5, or that they're non-squares modulo 5. And you can go through the whole recipe for conjecturing moments of L functions in those families. So take the L's that are squares, the d's that are squares mod 5, and also satisfy the other condition, modular conditions mod q, and that's going to be a family. Calculate the moments there using the recipe, and now do the same thing but with the d's that are non-squares mod 5, the recipe. Well, what you find is you get exactly the same answer, except in the arithmetic factor, the factor associated with your prime 5 that you selected is the only place that the thing's different. Otherwise, everything's exactly the same. It's only different at the Euler factor for the prime that you chose to analyze the distribution of twists mod that prime. And so the answer you get is just this. This is for the prime q. It's just q plus 1 minus aq over q plus 1 plus aq square root. And so that's it. So, for example, so here's data on 3 elliptic curves, E11, E19, and E32. Now, E32 is kind of known as the congruent number curve, and it has complex multiplication, which means that a lot of APs are 0. The APs are 0 whenever P is congruent to, looks like 3 mod 4. Whenever P is congruent to 3 mod 4. It's 0. The AP is 0, which means in this formula, that's 0. So these A's are the A's that appear in the Dirichlet series for the original elliptic curve. And so when this is 0, then this ratio is 1. Okay, so every place you see a 1 here, that corresponds to A is 0. And so the prediction in those cases is that the ratio is 1. You have the same, it's equally likely that you're going to get rank 2 from a quadratic twist that's a square modular your prime or not a square. Okay? And here's the prediction, the RP that we predicted. Here's the data up to for hundreds of millions of curves. The ones are really spectacularly close, as you can see. Now here, this one's, you can tell, that's obviously square root of 2, right? And so that would be a situation in the E32 curve, A5 must have been, whatever. But that resulted in that thing being a square root of 2. So these numbers are all square roots of integers, or 1 over square roots of integers, as the predicted ratio of vanishings. But what you see throughout this table is uniform good agreement for this conjecture. And I claim you can't really get this conjecture another way than going through moments and Birch, Swinnerton, and Dyer, and random matrix theory, identifying that rightmost pole as s equals minus a half. That's why you have that square root in that formula, right? This square root here comes from the fact that the pole of the moment generating function for s powers of orthogonal matrices is the rightmost pole is at s equals minus a half. Yes, yeah, it is, because, yeah, and basically what happens is that, in fact, there's, so you know how I talked about, well, in the recipe and stuff, you have lower order terms. So you can go down to, you can actually do this, you can take into account then secondary terms, and we actually did that, and the data actually improves. But basically what happens, your square root error term is present in all of these things with 1. And so these should be sort of accurate to like square root, the square root that we believe in the moments conjecture, right? That square root there. Whereas for all the other, for everything else that's not 1, then there's a lower order term that's 1 log smaller. So basically the agreement here should be around 1 over the log of the number of points that you took, which in this case is like 10 to the 8th. So that's why you see agreement to like 2 decimal places, 1 or 2 decimal places everywhere else in the table, is because there's a secondary term. And if you put that in, then you actually get even slightly better agreement.
In your 500 example that you made, how much of them are CM?
In the 2000? How many are CM curves? I don't actually know. Does anybody know? How frequently do you get CM curves? So the CM curves, let's see. So it's when you have a Hecke character, right, of I don't know. I can't think. But even for the CM curves, it's only when the a's are 0 that you get that. So here, where a is not 0, you're back to the yes. Yeah. Okay. Now, we try to do this for rank 3 as well, and we're unsuccessful in actually predicting the number of rank 3 vanishings. We can't really sort this out because we can't separate sort of the size of Shaw from the regulator. We don't know how to do that. There's some mysterious connection there. And so we don't know how to do that, but we can do the experiment. Okay. And so in this case, the relevant thing is to calculate the moment generating function of the derivative. And that turns out to have its rightmost pole at minus 3/2 instead of minus 1/2. And so, so you can still, even though now we don't even know like the right order of magnitude of this thing, but you can still take this ratio and all the unknown stuff cancels off. And now you have the same prediction as before, but with a 3/2 there. And now here the data, here you don't have the sort of theta series to give you like the great data. But here's a small amount of data for the congruent number curve. For prime, let's see, rank 3s, let's see. Oh, this is the prime that you're sorting by. This is the thing's a congruent number. This is the prime you're sorting by. This is the number of rank 3s in the square residue classes, and in the non-square residue classes, the ratio, and the random matrix prediction. And it's not bad, but the data only goes up to, it doesn't even say here, does it? The data doesn't go all that far. But it seems like it might work here too. Now you can also do, you can do the exact same thing, but for what if you started with a modular form, cusp form of weight 4? So it's not an elliptic curve anymore. It's just start with a modular form of weight 4. Let's say that has integer coefficients. Okay. Now there's a formula like the Konen-Zagier formula, but now it's going to involve a now the formula now has a d. No, wait a second. Oh, God. Has a d to the 3/2. Yeah. So now for weight 4, if you have a weight 4f, and then you take LF at whatever the central point is, 2, thank you. It should just always be a half. Then you get sort of some kappa, again, times some c of d squared, and now it's over d to the 3 halves. Before it was d to the 1 half. For weight 4, this becomes 3 halves. If it was weight 6, this would be 5 halves. In general, it's a k minus 1 over 2 down here. So now you do the same exact stuff. The probability that this thing's smaller than 1 times kappa over d to the 3 halves is going to be 1 over the square root of d to the 3 halves, which is 1 over d to the 3 quarters. And now when you sum d's up to x, 1 over d to the 3 quarters, you get around x to the 1 quarter. So in fact, for weight 4 cusp forms, when you twist by quadratic characters, there should be around x to the 1 quarter vanishings. But now if you went to weight 6, this would become a 5 halves. And when you take its square root, you're going to get a 5 quarters. And then when you sum it, it converges. And so we expect only a finite number of quadratic twists of a weight 6 cusp form, or weight 6 or higher, to vanish. And you can also do the same, oops, what am I doing here? Same thing in arithmetic progressions. So here's go to the LMFDB, look for a cusp form of weight 4 and level 7 that has integer coefficients. And then you can do the same kind of experiment here. Yeah. And many other scenarios where this idea has been worked out and could be worked out. So Ian told me yesterday he's going to look at this with Siegel modular forms, didn't you? Is that what you said? And Mark Watkins has done stuff on this with symmetric cubes, and Gonzalo and Nathan Ryan have done some things also with Siegel modular forms. Okay, thank you.